Against this, so our disadvantages of this approach would be that you have to have a really a high capacity model, and your data set also needs to represent everything you might encounter during driving, so it needs to be really large, but at the same time also very diverse. And this, of course, makes the training really hard. And like those approaches are, of course, known to lack interpretability, and this is, of course, really important for the domain of autonomous driving, where safety is key. And the third paradigm is direct perception, and this tries to strike a nice middle way between those two previous approaches, where you take your sensory input and train a neural network to learn low-dimensional intermediate representations of your environment. And those are then used with your vehicle controller. And this is now 3 years old. This work was where they first proposed this approach, and they evaluated it in the racing simulator talks. And pros of this approach is, of course, you have a compact representation, and all of those intermediate representations are interpretable. And disadvantages of this approach until now, it has been really only evaluated for highway driving, which is a rather easy setting, especially compared to about the complexity in urban environments, where you have road junctions, traffic signs, and traffic lights, and so on. And they also only use a single image. So basically, what you're then doing is throwing all the temporal information that you have in sequential input, such as video. You're throwing this away and not using it for the prediction. So what we wanted to really focus on in this work was the last approach in here and answer 2 questions. So first, how do we actually use this in complex urban environments? And second, do we have any benefits from temporal information in video? So this is a high-level overview of our approach. We take in video input as well as the directional input. In this case, it's straight, right, or left. And then we use a neural network to learn affordances. And affordance is defined as attributes of the environment which limits the space of allowed actions. So those are exactly those representations that we want our controller to operate on. And if we then consider the problem of urban driving, what you actually want to do is drive from A to B as fast, but at the same time as safely and comfortably as possible, and also avoid infractions such as driving on the wrong lane, driving on the sidewalk, running a red light, or violating the speed limit. And of course, you shouldn't collide with other vehicles, hitting other objects, or even pedestrians. So those are 3 exemplary situations out of the urban driving simulator CoRL. And marked in red here are all the objects that are actually important for our driving decision. And also in white, you can see the position and the orientation on the street. So then we define our affordances. We have 3 continuous affordances. So this would be the distance to the center line of our lane, the relative angle to the road. So this is position and orientation on the street. And also the distance to the lead vehicle. And then we also have 3 discrete affordances, which are speed signs, traffic lights, and a hazard stop. And as you can see, we only have 6 affordances, but at least for the scenario of CoRL, those are holistic. So we can basically every situation that we might encounter in the CoRL simulator, we can model with those 6 affordances only. And this is a high-level overview of our agent together with the simulator. So down here, CoRL simulates the agent in our environment and calculates the current image as well as position. And then we use the position in CoRL's high-level planner to calculate or to give us the directional command. So at intersections, that would be then straight, right, or left, depending on where we actually want to go. And those are then fed into the perception stack, and we calculate the affordances. And in the controller, we calculate the control commands and send it back to the agent in the environment. So to zoom in into the perception stack, what we're actually doing with the image is we're applying a feature extractor, and in our case, a CNN, and save this feature map into memory. We save the last n feature maps in memory, and n is determined by a hyperparameter search that I'm going to talk on more later. And followed by this memory, we have task blocks. So those are task-specific layers, and each affordance has 1 task block. And they can be either unconditional or conditional, depending on whether they need to be conditioned on the directional command. The controller can be split into longitudinal control, which is gas and brake, and lateral control, which is steering. And if we want to zoom in even further, this is the perception stack, and I especially want you to focus on the connection between feature map and the task blocks. So here you can see some task blocks are connected to every feature map, some are connected to only every other feature map, and some are only connected to half of them. So basically every task block has its own temporal receptive field. And also here you can see in the illustration the directional command acts in the conditional task blocks, which are relative angle and distance to the center line, acts as a switch, which is in training basically specific sublayers in the task block itself. So and how do we, first the controller. The longitudinal controller is split into different driving states. So this looks like this, where, for example, have the most important one would be hazard stop, where we just apply the brake fully. But we also have, for example, a following model where we have an actual control model to follow the vehicle in front of us. And cruising, there we have a simple PID controller. The lateral control is done by a geometric path tracking controller, as well as added damping. And how do we actually get then the parameters of both vision and controller? So we frame the whole problem as a multitask learning problem, since we want to learn different affordances, but still related affordances. So and then this also makes it not only more robust, but also really fast. So a single forward pass through the whole agent takes only 50 milliseconds for the whole pass, which is well within real-time requirements for autonomous driving systems, which is approximately at 100 milliseconds and below. And to train, we use our controller operating on ground truth affordances, and then it's driving through the Kala town, and at intersections, it's randomly deciding where to go. For loss functions, for the discrete ones, we use a class-weighted cross-entropy, which is really important because we want to put more weight on the rare occurrences in our data, which would be, for example, a hazard stop, which doesn't occur as often, like, for example, speed signs. The continuous affordances, we use just MAE. And then we conduct a hyperparameter search for our task blocks, where we vary the type, the nodes, or the number of nodes, and the temporal receptive field to actually find the best suited task block. For the controller, especially for the PID controllers, we start with heuristic rules like Ziegler-Nichols as a beginning, and then from there we manually tune. For the other gains, for example, in the following model, we start with a reasonable guess and manually tune from there. So now on to the results. So first off, do we actually gain something from using video instead of a single image? And so because results tables are always really boring to look at, I just want you to notice here on the right side, the first 3 affordances, positive relative change is good. And for the 3 last affordances, negative relative change is good. So you can see every single affordance profits of using video instead of images, which of course makes sense. And especially relative angle seems to profit a lot from using video instead of an image. And then we actually calculated our agent against other agents on the Kala benchmark, where we have a training town, which we use to collect our data set, and a testing town, which our agent hasn't seen before. And we have different tasks, such as driving only straight, driving 1 turn, and driving to an arbitrary position from an arbitrary starting position. And as a 4th task, that's the hardest task in this benchmark, you also have added dynamic obstacles, such as vehicles and pedestrians. And also, there are different weather conditions, ones for training and also for testing. We evaluate against the baselines from Kala. Those are namely modular pipeline, the conditional imitation learning approach, and reinforcement learning trained by using A3C. And again, here I just want you to focus on the right side, where we actually evaluate how well our agent is able to generalize. So on the new town, as well as on the new town with new weather. And what you can see is that we're performing quite a bit better than the baselines. And the nice thing about such work is that we actually can show how our agent is performing in the environment. So here you can see it's approaching a red light and correctly slows down. Switching back to green, continues. Here it needs to go right, so it's going right. And here it just needs to keep on driving straight and just keep the lane. And you can see that it's able to do this also quite steadily as well. Here we approach a vehicle, we slow down when we close to the vehicle, and we also speed up again if the other vehicle is speeding up as well. And here you can again see we're keeping the distance rather steady, so which is also a good attribute to have. And on the next one, here you can see a pedestrian carelessly walking onto the street, but we're still able to stop for him and continue driving, so we avoided a collision quite nicely, and here we stop again for the red light. And of course, because we are also able to obey the speed limits, we can also test at different speeds according to the speed limit. So here's a 90 zone, so you can see here it's still able to drive quite safely. Here's a 30 zone coming up, so we need to slow down. Here we need to go left. Then there's a 60 zone coming up, and a 30 zone again. So, and now to like the favorite part of this work for me was we can actually show what the agent is paying attention to, and you can do this quite nicely. So here you can see in green where it's actually paying attention to when predicting the red light affordance. And green means red light equals false, so the prediction equals false. And when it switches to red, that means that it's predicting red light equals true. So you can see it's paying attention to the sides of the roads where the traffic lights are also expected to be. And now, next up, there's going to be a red light. And you can see it's focusing its whole attention on this red light. And of course, you can do the same thing with hazard stop as well. And from the left is going to be a pedestrian walking in. And you can actually see how it's focusing on the pedestrian's shadow at first. And it's predicting still hazard stop equals false, so if this starts playing. And you can see that the color is switching to orange. So this indicates that it's about 50% sure that there's a hazard stop coming up. There you go. And throughout the whole sequence, it's going to focus on the pedestrian and correctly outputting hazard stop equals true, because the pedestrian is in close proximity to our agent, and it's correctly predicting the hazard stop. So to summarize, we implemented a direct perception approach targeted towards urban environments. We predicted a compact conditional representation which handles speed signs, traffic lights, and is able to do smooth car following. Compared to the best line, we achieve a 68% improvement on the color benchmark in goal-directed navigation, and are 3 times less, or 3 times better in avoiding car crashes, and on the color benchmark also 10 times less likely to hit a pedestrian, which is a good goal to have. So, thank you.
Thanks so much. We have time for 1 or 2 questions. Yes, please.
So thank you very much. Can you tell us what do you get from this high-level planner for Carla?
So in this case, we get generally when we're driving on a straight road where there are no options. So also for example, you're approaching a left curve, but there's only the option to go left. We also just receive go straight or just follow the lane, right? And at intersections, we get either go straight, left, or right. Of course, you could imagine like more complex environments, right? So, but in at least for now in Carla, you can have only such simple intersection. So it's only 3.
Other question? Yes.
Hi. Thank you for an interesting talk. So for the traffic light recognition, you identify that they're on the sides. So for places where the traffic light might be above you or next to the junction, you'll need to retrain?
I mean, I actually didn't test this, so this would be really interesting whether it's still able to recognize this correctly. But also, I cannot go into detail into this, but the way we acquire the ground truth affordances is that we also acquire to have a certain distance where the red light is actually important for us. So if we're too far away from the red light, then it shouldn't concern us yet. So, of course, this would need to change in the implementation if you wanted to do other traffic lights, for example, on the other side of the streets, which are still important for you. So this is for future extensions, maybe. Thanks.
Okay, thanks very much. Please.